let's say the convolutional neural network building blocks, and I will maybe just skip that because it's good to know, and I think you can know from the videos, but we can talk maybe more general. The second part of week 3, which is about self-supervised learning, it's about creating, let's say, these vectors, these embeddings, these blatant representations, right? So how do we kind of do that? Why do we do that, etc.? So I'll share my slides, and these are the same slides that we've used for, our videos, but we'll quickly go over those. Yeah, so usually what we're used to working with is like an organized data set, right? So if you have, say, ImageNet, you will have like a lot of these images labeled with the class that they have, and you then can train a model. But that's not how a child really learns, right? That's not how a child learns to, let's say, understand concepts of a cat versus a car versus a tree. So, so it's not just supervised learning, right? It's not that we always show them a photo of cat and say cat. It's not always we show them a car and always say car. To some amount it is, but it's more than that. There is some amount of reinforcement learning through behavior that they learn, and then there's also some unsupervised learning, some learning that just comes by itself because of how the brain is wired, right? Because of the fact that it's an animal brain. So, supervised learning, I mean, the label data that we have is just the tip of the iceberg, like on the internet. There is like a lot of unlabeled data, let's say your Instagram data, the videos on YouTube. You have very sparse labels here, right? You have just maybe the description and the title of the video, but there's so much information in the pixels of the whole video. So this is still, the iceberg which is inside the water. And Jan has this cake analogy, and it's very famous. Essentially, he's saying is the iceberg is, the part which is sticking out is just the the cake, the top of the cake, the icing of the cake. And the unsupervised learning is the actual cake, the, the full cake. It's the supervised learning is just this much because it's the iceberg which is above the water. And the cherry is essentially the RL because the signals are so sparse. So it's a cherry on the cake. And this is how I think it's a good worldview, I would say, of, let's say, how much signal is present in any of these layers, in any of, let's say, unsupervised or self-supervised learning, the supervised learning, which is the icing, and the cherry, which is reinforcement learning. And how can machines learn like humans from unlabeled experience? Now, this is an interesting, thought experiment. Like what we're saying is, if we have, let's say, a 1024 cross 1024 image, we have, if we flatten it out into a vector, we have, more than 1 million dimensions. And if we sample random pixels in this number of dimensions, you will never, I mean, to be mathematically correct, you will say almost never, but you will never really get a face, right? If you do get a face, that's like a matter of a huge, let's say, a probability game, like 1 out of 1 million. So this must be worth something then. So yeah, like of all valid images in this tiny vast ocean of noise. So if we can take any random number on this image, it can create like so much garbage mostly. But let's say this small tiny island, which will create, let's say, faces or natural images that mean something to us, is a very small part. Is, so how do we kind of think about that concept? And one way to think about that is this crumpled paper analogy. What we're essentially saying is this manifold, right? So here, though it's a simple line, in some space, it can look like a very crooked line. But when you transform it into another space, it looks like a straight line. So the it's like flattening the manifold so that we can understand the true structure. And this is what we are trying to do with this unsupervised learning. We're trying to untangle it. We're trying to represent only the semantically meaningful attributes of your data, right? So, we've looked at this face manifold where we can change the gender, we can change the mood, we can change the eyes. Oh, we haven't looked, but we'll look at it in more detail in week 7 when we talk about generative model. But essentially you can change this attribute, and based on this attribute the corresponding face changes. So these are the meaningful attributes which we want those, let's say, low dimensional vectors to represent. So the face manifold, yeah, I mean, this is going outside the face manifold. When we try to generate images, we can still land on images which look like this, which is just outside the manifold. So this is essentially the manifold concept, right? The idea is very simple. You have high dimensional data, but what you want to do is you want to represent this into a lower dimension. And you can, why? Because of this argument that a lot of this is essentially not useful, right? So not all your million dimensions are actually useful because you're projecting it onto a 2D image. This is why we are needing so many, let's say, pixel values. But the meaning that is contained in that image is of a lesser dimension. How many dimensions? We don't know. Because how many dimensions does it take to render out, let's say, a high quality face? Or a high quality, let's say, digit. It depends. So different objects of different complexity can have different, let's say, number of true dimensions, inherent dimensions that they need minimum to represent them. Right. And it is also a matter of how we're able to untangle that representation, how we're able to represent these meaningful attributes in a way where, it is orthogonal, where we can use the least amount of, let's say, vector components and so on. So again, the idea is very simple. We have a high dimensional image, let's say 1024 cross 1024, and we want to represent it with a lower dimensional vector. And this is what all of, let's say, unsupervised learning is all about. And the low dimensional vector that we want to represent it with should have certain characteristics. One of the characteristics is that in this space, it should have, let's say, a measure of distance. We should be able to say, okay, this vector and this vector, what is the difference between that? Because we might want to know the distance between images, because we might want to define similarity between them. Also, things like, the triangle equality, inequality has to hold there. The sum of any two vectors has to be, let's say, greater than the third one, if it's the triangle. And what else? I don't remember. There's another one. So, right. So mathematically, it has to hold these characteristics. If it does, then that vector is meaningful. And this is what it is all about. This is what we want to do with all of JEPA, with metric learning, with triplets, right? With all of that. So, any questions so far? Like, we discussed an important concept, and I want all of us to kind of understand this because it's the basis of like a lot of things that we do. Anybody wants to kind of summarize what I just said? It will help you remember and articulate and linearize your thought. Okay, Ankit also joined. Hi, Ankit. Hi, Pratim. Yeah, so what we're doing is we're kind of, I don't know when you joined, but we're going over, let's say, this notion of unsupervised learning. What we want to do, we want to find these low dimensional vectors. What we can do with those vectors, we'll talk about later, like why are we doing unsupervised, etc. But yeah, what we're after is this low dimensional vector representation from a high dimensional data point. And that high dimensional data point can be an image, a video, a piece of music, voice, etc. So, any thoughts? Dipen, Harsh, Danina, Kunal, Jayaprakash, who else is in? Yep, Pratim, Ankit. Anyone? Especially like the TS, right? Like, what is your understanding of, let's say, unsupervised learning? or self-supervised learning. So what do you want to get as like the output? Then obviously the understanding is that you don't really need explicit labels because the data itself has some structure which you can exploit to get a signal to kind of again measure this, let's say, similarity or dissimilarity between low dimensional vector representations. But what is like, yeah, how do you think about it?
Can I go, Arjun?
Yeah, Depan, please.
So how I understand unsupervised learning is like we try to generalize whatever data that we have been given with into some sort of like, parameters. So, and like converting those high dimensional vectors, which are very rich in data, to lower dimensional, which is basically extracting the useful part and leaving out the other part, is basically one step in that learning and parameterization of the process that we want to actually mimic. So yeah, that's my understanding of
Yeah,
how.
I think it's a perfect understanding because think of it this, right? Like what you see is a picture of my face. And in here, like how many muscles does my face have? How many skin texture, like texture is one parameter. There is lighting. You can represent lighting, surface reflectance, material, glossiness, all of this, right? With lower dimensions. So if you could actually create, let's say, a model of my face and render it in 3D, you would not need a million dimensions. It'll be much lesser. So definitely my face lies in a lower dimensional space than a million dimension if you want to even create an image out of it. So yes, it is all about, and of course, then how good or bad it is depends on how good it is at. And then, okay, like what is your understanding of what can you do with that vector? Like why are you interested in untangling this representation of these million pixels to this underlying true, let's say, image creation process of material, surface reflectance, BRDF, all of that. So why do you think we want to do that?
Or is it to assess the true structure, like as you said, the manifold
But
basically.
what is the use case? Why? What is the advantage? Why do we want to do that? Why? How does it help us?
Maybe if we learn the process of how it's made, we can actually, like in downstream tasks, use that process to create more advanced as let's say how generational model work is that they kind of learn how to reverse engineer it and then they actually try to, maybe follow that process to generate images, videos, or whatever in that.
Yeah, so yeah, one way is to like you went on the generative side, but even on the discriminative side, meaning what you can do is you can learn something with this unsupervised approach, and then you're able to generate a vector, a low dimensional vector. So all you then need is a smaller model on top of that to then do whatever you want. So you don't, so you can compress your high dimensional data into a low dimensional vector and use a small model. And that is what you do in reality. You use your Dino V3, you use your VGGNet, you use your ResNet, any model you use, you're giving it a big image, whatever, 512 cross 512. So lots of dimensions, 250K dimensions. And then it gives you a small vector, a 1024 vector, and then that is your low dimensional vector, which you can then use for your downstream tasks. For the simplest thing you can do if you don't have any labels is clustering. You can know similarity. So now given something, you can do a RAG, you can do a lookup. And that is what this week was all about, right? So what we were doing was we were creating this lower dimensional representation from our SIGGRAPH chunks. And then we have our vectors, and then we're able to do something. We're able to retrieve, we're able to do clustering without any labels. But now, if you have labels, if you do label those chunks as good or bad, or like different, let's say, classes, then you can still be able to learn some model on top of that, a classification model on top of that for cheap, for lesser number of labels because the model is smaller. Yeah,
Arjun,
yeah,
one question.
yes, Anish.
Uh, like we represent higher dimensional vector or image into a lower dimensional vector, but how do we know that this lower dimensional vector is capturing all the useful information correctly, or how faithful it is to the original one?
That's a great question. I will answer this question, but in the meantime, somebody knows something about it. I'll give you a hint.
In
Think.
supervised case, maybe we know we can compare with some set of labels, or like we know what is the truth and we
Yeah,
can compare with it.
no,
But
there's a better way.
unsupervised,
Yeah, so for example, think autoencoders. Like, anybody know where I'm getting at?
Is it just
Okay.
the L2 loss with respect to the original image once we reconstruct the image?
Yeah, so what he's asking is, Anish is asking, like, how do you know that the vector that you created is good enough? What if you lost too much information? Did you lose the important information? So one way to do it, what Aditya is saying is to then do the reconstruction, meaning you have, let's say, a high dimensional data point, you reduce it to a low dimensional object, and now this low dimensional object should be able to recreate that high dimensional object, right? So you should be able to then generate from this low dimensional vector. That means that you have captured all the important things. And usually, this is one way to generate your low dimensional data. What you want to do is train an autoencoder. So you have your, so it looks like an hourglass, right? It looks like there is a big side, and then that big side, like this is your high big data. Your data then becomes small. This is your low dimensional representation. And then, so this is your encoder, and then you have your decoder, right? The decoder is then going from small to big. And then once you've trained it, you throw the decoder out. And what are you training in the decoder? At the end of the decoder, you are training an L2 loss, meaning you want to reconstruct the input back. Whatever is your input, you want the same as output. And because you're going through that bottleneck of low dimensional vectors, you know that, okay, whatever is in there should have information. Otherwise, how is it able to reconstruct the image back? So
Okay,
that
yeah.
is one way. Anish, does that answer your question?
Yeah, that makes sense. Yeah, got it. Thank you. Yeah.
Thank you. That's a good question. But again, like what is a good representation is an active research field. It depends on so many other questions. What do you want to do with that representation, uh, and so on.
Yeah, right.
But yeah, it's a very interesting question. Anything else, guys? Yeah, Meena, maybe your video is moving. You can switch it off until, yeah, thank you. Okay, Harini is also joined us. Hi, Harini.
Hi, Arjun.
Hey, so we were discussing vector representations, we're discussing unsupervised learning, how to kind of, what does it mean to have a low dimensional representation of a high dimensional, object of a data point, and why do we even want to do that? And yeah, our assignment this week was to kind of do this in real life. So we want to compress these chunks into low dimensional vector representations and then uh, try and retrieve them, try and cluster them. So yes, and we'll talk more about that. But yeah, any questions? Any other thoughts so far?
Yeah, Arjun, one question
Yes, Pratham.
regarding this unsupervised learning. So finally, so far, whatever we have learned is that in supervised learning, we generally train the network, and finally we get some kind of loss number, and based on that loss, so we try to again fine tune the weights and come up with the good weights for the network. And that's how,
Yeah,
if we know where we are going, like if we know the
yeah,
destination, the marking of with respect to each
loss.
of the
Yeah.
images, then we will be able to understand what is the loss, and from that we will be able to figure out. But in
Yeah.
unsupervised learning, we don't know anything, right? So
No, no.
what
So we do
the
know, right? We know the image itself. So what we're saying is, because we're doing this autoencoder business, for example, we're saying, okay, we want to go to a low dimensional vector representation, and from that we want to reconstruct in our decoder. And so what we have is the input and the input itself. So it's just a smart way of getting a signal. So you do need a signal. We will still use the backprop. We will still use, let's say, MSE loss, a per pixel loss, to then backpropagate and train the model. And once the model is trained, we can throw away the decoder because we don't really need the decoder. Our goal is not to recreate an image. Our goal is to just get that low dimensional vector representation. Does that make sense? Or do you have any follow-up questions?
no, I got confused actually. Like finally, we don't have any label, right? So
No,
we
but
do
listen, yeah. So
autoencoding.
I mean, before I try, anybody else wants to try to, okay. So see, like we have our image, right?
Yeah.
Let's say, and now the loss is still on the image. Like we're just saying what we want out of the network is still the same image. Or let's say we have some text, and what we are saying is we want the same text as output. Or if we have text, we are saying we want the next word as output, right? So it is still
Okay.
unsupervised because you're not wanting to label it, but you still have signal because you know that, twinkle, twinkle. So after twinkle, the next word has to be twinkle, kind of a setting. So that is still your signal. That is still your loss. You will penalize if you don't get that.
Okay. But then you mentioned that we'll remove the decoder from the network. So after that, like what is left out in the network is that we have some image, for example, and we have trained the network to learn about the image. So that is what is left out, and that is what we want to achieve actually, right?
Depends on the use case, right? In case of images, yes, but when we talk about LLMs later, in that case, interestingly, we have removed the encoder and we've only kept the decoder, right? So that is why it's the so
Okay.
yeah, so we'll talk about that.
Okay, got it. Thanks.
So here, so I mean, just to give you a little bit of context, is we started with sequence to sequence in the sequence models, and then what happened was there the encoder was not needed because we'll talk about, and then we only kept the decoder. So it's
Okay.
because our goal was then to generate, right? Because we want to generate text. We don't really want to encode text, do so much translation work. We just want to generate text, and that is what the GPT is all about.
Okay.
Anything else, folks? No, so then maybe we can quickly finish the rest of the slides that we have in the videos. Sorry. Yeah, so and then so if there is a manifold, and if we then start to step outside the manifold, and the manifold, remember, in this high dimensional space is a very tiny, tiny part of this huge space, right? And if you start to go even outside the manifold a little bit, then you start to get, to data points like these. So yeah, we spoke about the encoder decoder, right? So this is what we were talking about. So you have your input data, you want to encode it into a low dimensional vector representation, and you can use a neural network to do that. And usually the dimensionality of Z is lesser than X, because what we want to do is we want to capture those meaningful factors in variation in data, right? So, like I said, for the face, we want to maybe understand the lighting, the material, the glossiness, the structure of the face, etc. Properties of good embeddings. So, yeah, so distance should mean similarity in the Euclidean space. So, in Euclidean space, distance should mean semantic similarity. If two vectors are close to each other, they should mean the same person. If two vectors are far away from each other, they should mean different classes. Mappability, of course, this is a basic. So we should be able to map any sample to valid points. Smoothness, interpolation should produce meaningful transition. In this case, the faces that I showed you, these are found by interpolation, and not all interpolated images look very realistic. So what it means is while interpolating in the Euclidean space, you're going outside the manifold. And invariance to transformation, deformations and transformations. So depends what kind of deformations are you willing to be invariant to, what makes sense for you. This is again problem dependent, but we do want to be invariant to a lot of different types of transformations. For example, if it is about, let's say, facial recognition, then I want to be invariant to the size of his hair, or the beard, or the lighting, or uh, age, etc. So all those are uh, invariances that I would desire if I am doing facial recognition. So we spoke about autoencoders. We said that autoencoders try and reconstruct the same image again, or the same input data point again, and we can measure a simple loss where, let's say, it's a four-layer neural network, and we then want to simply measure the reconstruction loss at output, and we can then decide to throw away the decoder. And note how this doesn't use labels, right? That was the whole point, because you are just using the input data itself. You can just download images from the internet and you can train your autoencoder. You don't need to label it, right? All you want to do is reconstruction. Reconstruction means reconstructing the same input again. And then, like I said, you can then train a small classifier on top of that. And now this classifier will be much smaller because your Z is much smaller than your X, because that is what we started with. So, and then, yeah, we discussed curse of dimensionality. Of course, it's very difficult to imagine high dimensional spaces, but high dimensional spaces are essentially spaces where there's a lot of space, right? So most things are really far away from them. And then finally, so this is a very interesting concept, and the math looks so complicated, but it's really, really easy. And whoever really wants to learn the concept, if you know about it and if you want to try and explain it, go for it, because then you'll remember it forever. Because I already know it and I can explain it, but anybody who wants to kind of take a shot at it quickly? No? All right. So what we're saying is that there is just this one network, right? You can call it two different networks with the same parameters. Essentially, it's just a copy. And after every training run, we do a copy. And then what we're saying is, I mean, let me come to the equation for later. Let me first, let's say, uh, let me first talk about it without, let's say, talking about the math. And this is the real Siamese network paper, right? And in this paper, what he did was he took this high dimensional input image. Uh, I think it was 28 cross 28. And then he had this 32 cross 32. And then he has these first layer activation features. So it can be like a question that, okay, to get this kind of activations to 32 cross 32, what kind of a convolutional layer do you need? But anyways, you get this convolutional activations, you get the second layer after again another after your max pool, and then you put it into a fully connected, and the output of a fully connected are just two neurons, right? Just two neurons as output. And now what you want to do is you want to give it images from the same class, for example, the image of the number 4, and you want those two images, those two vectors to be as close as possible to each other, meaning you want them to be the same. And then you want to give two different classes, let's say the number 4 and the number 8, and then you want to push it m apart. So they may be, so they may be far away or they may be close to each other. You want to push it at least m apart. And the way I visualize it in my head is an m-dimensional ball or m-dimensional circle, right? And we are, let's say, at the center, and we want to bring all points which are like that to the center, which are all fours. I want to bring them to the center, but everything which is not four, I want to push them at least m distance away from me, right? So that makes a circle. The locus of that is a circle. And that's it. So if it's already far away, then there is no loss. But if it's in between this, if it is between me and m, then I take the distance between me and m, which is dw, so this much distance, and then the remaining distance m, and I just push it to the top of the sphere, because I don't want it to be everywhere, right? I want it to be only like, so that I can then put threshold, so that I'm not putting. And so what happens when you do that is, when you force it to lie, let's say you don't give it penalty for like infinite penalties, it creates vectors which have good properties. So it will bring these same class vectors close to each other. It will bring these different class vectors far away from each other, at least m distance away. And you want to penalize things which you don't want to penalize things which are, already a little bit far away. So this is called like a hinge loss, meaning there's a cutoff to the loss. You don't want to penalize points after that, because you're happy, because you're able to put a threshold. So it doesn't make sense to penalize things like in a linear way, because there is no such definition. There is just a binary problem: the current class or not the current class. And to do that, you want to employ a loss like this hinge loss. And if you want to do this mathematically, all it is saying is, okay, when let's say it is the same class. So when it is the same class, you want to minimize just the distance between them, and the distance between them. So you have x1 and x2. X1 and x2 are the two inputs, and y is the label, and w are the parameters. And dw is the distance between these two vectors, right? Between x1 and x2. So when it is the positive class, meaning when y is 0, meaning when they are of the same label, then I want this dw loss, meaning I just want to minimize the MSE loss between them. And then and then obviously this term is 0, so we don't need to worry about this term when they're of the same class. But when they're of the different class, then we say y is equal to 1. And then y is equal to 1, then this term becomes 0. And then this term, look what we're doing. We're saying the maximum distance, it has to be the maximum of 0, comma, m minus dw, right? So m minus dw is what? It is the distance of my current, of the radius of this margin m and the distance between them. So, so essentially you're saying, okay, you only want to minimize you want to give this m minus dw.
Sorry, I have
Yeah,
a question here.
yeah.
So, in this case, the loss that is being propagated, so it's basically shared between both the networks, and that is the same, like the backprop is basically the same between the
That's
both
a great
layers. Is that
question.
how?
Yeah, so what in practice, what you do is, what do you think you would do in practice? Suppose you have big
Uh,
networks, you have, shortage of GPU. Like, what would you do? Because you'll have to keep two copies. What would you do?
uh,
So what you can do, for example, is you can forward propagate within the same network, because all you
right.
need to do is you need to, remember just the activations of the two. And then you can back propagate, and you can back propagate through the same. You can accumulate the gradients, and you can then just do an average. So you can think of this as a batch.
Oh, I see. Okay.
Does that make
Uh,
sense?
but so I mean, if you're saying both the networks would be treated as two different batches, so it will alternate between runs, and we won't do the same network every single like time. That's what you're saying.
Yeah, so for example, suppose there is no batch. Suppose we're doing every image backprop. You can do that. It'll still work, but not as well. So in that case, you can forward propagate with one pair first and then backpropagate and train it. And so let's say we put a positive pair first, you compute the loss, you train it, and then you put a negative pair, you again forward propagate, backward propagate, you train, you update the weights. Or what you can do is, and what you do in reality is you create many such pairs, and creating those pairs itself is something to think about, because positive
Mm.
pairs are limited, because let's say you have a class with 10 examples, but negative pairs are way more, right?
Yes.
Because you can have negative pairs with all the different classes. So which negative pairs should you work with, and what kind of a batch should you create, and more on that later. But
Mm.
yes, you can either, let's say, just do this, which is just forward propagate, backward propagate, train, or you can do that in batches. You can create many of these pairs, forward propagate once, create the loss, and then backward propagate in one step. But we'll
Okay.
talk about that also when we talk about a few methods, either yeah, I think in week 4, beginning of week 4 or end of week 3.
Okay. Sounds good.
But did you get like the uh, the intuition? Like you can also train like how you were talking about, right? You can just take this positive pair, forward propagate, compute the loss, backward propagate, train.
Right. Okay.
But that's not the
Yeah.
most efficient. Essentially, I mean, I'll give you the big picture is because we want to do it for a lot of pairs, and we want to do this thing called as hard negative mining. What does it
Mm.
mean? It means that we're interested in only the hard negatives, because the negatives which are beyond this M are not giving me any loss anyways. So they're not giving me any
Right.
signal. So,
Yeah.
but then there's another detail here. You don't want the too hard negatives, because that destabilizes the network. So you don't want anything which is like too close to that positive pair. You want to keep another margin and then take from, let's say, the ones which are close to the surface of the sphere or a little bit inside, right? So there's a ring, the Goldilocks zone, where we want the negatives from. And
I
how,
see.
because you don't want to do it again on the entire data set and keep all of that in memory, and your GPU memory is limited. So you want to do it based on a batch. So you want to, let's say, stuff your GPU with 1,000 images, with 100 images. And from these 100 images, you can create a bunch of these pairs. And creating those pairs is also, again, something we'll discuss in more detail, because you have to create them carefully to be efficient. And then you can compute the loss for that and back propagate in one step.
Got it. And I mean, as I imagine that the training goal, right? It looks like a k-means classifier in itself. Like you have the nearest neighbors that we talked about, where you create vectors which are close to each other and they're different from each other. So is that how it also stores it in the memory so that it can easily pick up similarities?
It's not storing in memory, right? It's creating these weights which have the ability to transform it into this space. But yeah, in this case, we are mapping it to the exact same point. But when we are,
Yeah.
let's say, doing an autoregressive method such as an LLM, in that case, we are trying to predict the next token. In that case, we're trying to predict what should come next. So it's not really, let's say, the exact same representation. It's not exactly then your k-means clustering concept. But in this case, yes, because that is the only signal we have from unsupervised learning. Is it
Right.
same or
No,
not? Mhm.
but okay, but we don't use the technique to visualize it. I'm not saying we use it to like store it, but do we try to visualize like during I mean because in unsupervised we don't know the ground truth. So visualizing during the training part is
No, so you cannot really visualize it. And again, that's a good question. So you can visualize it using, let's say, PCA techniques. You get an output vector, and then you try and look at the first few PCA dimension, let's say. Or there are techniques like UMAP and I forgot the other one, t-SNE. So you guys have heard of, any of you have heard of those? So UMAP is by
I
Hinton.
think UMAP was something that came up last week.
Yeah. So
I
UMAP essentially is a way, and t-SNE, like I said, yeah. So UMAP and t-SNE are, yeah, you can see some maybe images. So you can then kind of see some clusters from, but the thing is, like Hinton says it himself, that in lower dimensions, yeah, you can choose now how to project it. So there's no real way of projecting, even if you are 1024 dimensional latent vector, there's no real way to kind of really see it and understand what is happening in that high dimensional space. So there are some techniques, but like I wouldn't kind of depend on them, right? So the only way to
Okay.
then see it is, okay, is it good enough for downstream task? What am I able to do with that? And also maybe some other clever ways of understanding what it is learning.
Okay.
Cool. Yeah. So we said, okay, if it's the same class Y0, if it's a different class Y1, uh, maximize distance up to margin M, push apart. And this is what, what Harini was talking about. It will eventually look a little bit like k-means clustering after it, trains and pushes them apart or brings them close to each other. And interestingly, you remember this network which I showed you? So you can do this at home. You can compress your 32 cross 32 image into just 2 dimension. And now because it's 2 dimension, you can visualize it easily, right? So you are now visualizing the images, the 2 dimension, and this is how they look like. So they just took the two, let's say the value which is coming out for 4 and 9. So some two numbers are coming out, right? And some two numbers are coming out. You're taking that as x and y, and you're just plotting them on x and y, maybe doing some normalization and plotting just the 4s and 9s. And they see that, okay, the 4s and 9s, the 4s which are really looking like 4s, they're far away. And the 9s are, far away from each other. But when you go close to, let's say, the boundary, then they start to look like each other. So these were interesting foundings that they kind of saw in the data. They also,
So
yeah.
sorry, the so another question that I have like is that what do we do to kind of balance between the bias and variance here, especially because we are deconstructing and reconstructing. I'm pretty sure that we'll be losing a lot of data. I think you already covered it a bit, but I wanted to just
So,
know if
you don't really lose too much. I mean, what happens when you do that autoencoder is
yeah.
that when you go down even to like lower dimension, you can still bring it up, but the images become blurry. Why do you think that happens?
Because we do lose certain features of the data, right?
Yeah, it's also because we have a MSE loss, right? So the MSE loss has
Yeah.
this tendency to kind of smoothen everything out. So
Yeah.
that is what it looks like. But you're still able to kind of get some low frequency details. And the only way to know it is to then use it for a downstream task. For example, the state of the art, let's say video model is VJEPA or VJEPA 2, and it is a strong backbone. And now you can use that and see if it generalizes on other data sets. And that is the main goal. Like you want to see if, but I guess what you're asking is like during training time, how do you know if you are overfitting or underfitting, right? So
Yeah. That's fine.
yeah, so again, like you're kind of doing that to your test set because your test set also has data and that has loss. And you can define a metric like if it so start with just loss and your test images, your model has to generalize. The embeddings have to generalize to your test set data. And that is the only way you would control, like in any other, even like when you do your normal classification models, right? So you want to select the model which has low loss, not just on your training set, but also your test data. And what is that low loss? Your reconstruction loss, for example.
Okay.
Yeah. So they also tried it on, let's say, images of 3D objects, and there they could show more structure, embeddings in 3D. And one real world example is suppose you want to do Face ID, right? So this FaceNet came long time ago, I think 2016, 2017. And what we want to do is let's say enroll people. We want to do Face ID on your iPhone. So now you cannot do a classification problem because do you keep changing your network? Do you keep increasing your classes? And that is not even the right thing to do, right? So how do you train a model to do that? And the way to do that is using the kind of techniques we discussed. The Siamese loss. In reality, they started with the triplet loss. This was when I was at Apple, like early 2015, 2013. So that is when they started to use. And in an iPhone, you may or may not know, there is also a depth sensor. And the depth sensor also captures visual features of your face. Also, like during, so this depth sensor is a time of flight sensor, and it captures the surface of your face geometry. And we can talk about details on how you actually do Face ID. What in Face ID, you don't really look at the full face, you actually look at patches of your skin texture, and that is different between all of us, right? So there's a fingerprint of those pores, those patterns that we have in our skin, and that is how they train those models. But the whole point is that you cannot do classification. So what you want to do is you want to have an enrollment step. When you buy a new iPhone, you have to like turn your face and do all that within their interface. And what that is doing is it is collecting a lot of information, it's collecting a lot of these images, and it is then converting this into a vector representation because they already have trained a giant model which is able to not a giant model, a small enough model which is on device, which is able to convert your face into this vector representation. And now whenever it gets a new face, it checks if it is similar to this vector representation. And this is how you would want to do a face ID kind of a problem, a real world face verification problem. So at training time, you would want to train all this, and at deployment, you just have a single threshold. There is no retraining needed. So that's pretty simple. And we already spoke about this concept of this hard negative, but what you don't want to do is you don't want to give it too hard a negative. Uh, and that's it for this concept. So before we start like the remaining, we have like 15 more minutes. Do you have more questions? Because that could be like more important and more interesting. Or anything else you want to talk about? And Harini, I mean, I looked up on a little bit on, the PID and MPC based, especially when you want to do machine learning with that, the different ways and things that people are trying. The people are already doing like a lot of research on that. So I don't know if you have also looked it up, but we can discuss it maybe next time. But yeah, it's again very interesting and there's some exciting work going on there.
Yeah, actually, so I did go and look up the, seeing if there's any models on this that are there, and did a little bit of research. So what I found out was, you're right, like there are already reinforcement learning or Bayesian optimization, etc., that people are using to kind of tune these parameters. But what is not being done is that I don't think it has been collectively or the relationships between the inputs, outputs, constraints, and the various parameters are not, there's no model that exists that can be actually just downloaded or embedded and then like do a search and then use it. So I probably have to, if
Yeah,
I'm having a use case in mind, I have to construct it on my own.
yeah.
Yeah. So
So
it's
what I found was like there are people who are trying to replace all of PID and all of MPC and all of that, right? So just do everything using a network. But then there are
yeah.
people who are trying to, like you said, like there's a lot of, let's say, value in what has been done over the years. Now, can we just make that better a little bit? And for example, I was just like Googling, there is ones where you wanna, for these, use like small language models, etc. So
Oh,
not sure like how useful these kind of things are, but yes, I agree. Like using traditional techniques with new techniques, they're not too much work, and it could be something interesting.
yeah. I have some follow-up questions, but actually I'll just write to you and then I'll share some resources and you can let me know your
Yeah,
feedback
I
on
will
that.
also look it up, and then maybe we can talk about it again next week.
Okay, sounds good.
And
Um,
I'm also interested to learn here, so yeah, do share whatever you have or whatever you find.
yeah. Yeah. Do you think it's a feasible direction for the capstone, or so maybe that's too big of a project to finish in
No,
like a
if
few?
we can narrow it down, right? Like what
Okay.
kind of a model we're talking about. A model can be as simple as an Excel sheet, right? So
Hmm.
it depends on how we wanna define the problem.
Okay. Okay, let me take a jab at it then. I'll try defining it in
Perfect.
a way.
All the best. I'm sure it can be done. Cool. Anything else anybody wants to add? Fast code people, how are you guys doing? People who are taking this course. Jaiprakash, Kunal, Denina.
Yeah, yeah. So, like Arjun, like I want to clarify one thing. You said that iPhone's face recognition like throws some 3D map on our face for facial recognition.
Mm-hmm.
So, the iPhone's sensor works well on when the light is low or it's too bright. It works on both. Like,
Mm-hmm.
so, how it determines that whether to let's say the
Yeah.
lightning is too bright on our face, so how it determines that
Yeah, so for example, it has this thing called as a time of flight camera. What it has is a laser. It shoots those lasers on your face. I mean, and then it gets reflected and it creates a 3D model of your face. So what I mean to say is, uh, iPhone front of camera. So, and that works in night, right? Because it's a laser pulse that is coming in. Uh, yeah, I don't see like visualizations of that. But what is happening is, I mean, the other way to do it, and some other camera manufacturers do it, is by adding a infrared lighting sensor, but it doesn't work in strong daylight, etc. So what you can do is you can have an infrared light, which your eyes cannot see. That is what we do inside cars. For example, in a Mercedes car, we light up the interior using infrared. So the user, a human, cannot see that light, and the camera can still see that light because the camera is again a near infrared camera. So that is one way to do it, but iPhone doesn't do that. It has a time of flight sensor.
so like it ignores like whether the lightning is a meaningful factor or not, or
No, it is a different way of measuring what is going on. So once again, I'll show you. It has an emitter. It emits a pulse and it checks what comes back. So it has an emitter. It is not just a passive sensor which is sensing photons of light. So it's a sensor like this. It emits something and it checks the difference of phase that is coming back because of the reflection. So you can think of it like a LiDAR sensor, but it is dense. It is still a similar concept of your LiDAR sensor, but what comes out is not a sparse measurement of your world, but a dense measurement of whatever's in front of it. But dense, but low resolution, maybe 320 to 40 kind of a resolution.
Okay, thanks.
So I had a question about the search methods. In this particular assignment, we used BM25 for ranking and then a semantic search. So depending upon the type of data that we're using, does the search type also change? And is it something that like when we do in ChatGPT or Claude, etc., is it automatically pick that? And when we do it, do we have to? When we do it on locally, we select the kind of search, right? We write the code for it in the back end and we determine the search algorithm. But how does these large LLMs kind of deal with that?
No, but your large LLM is not doing any search, right? I mean, it is just looking at the concept, your context, maybe summarizing the
No, no,
context.
rather, I mean like uh, no, there is an algorithm that retrieves the data, right? And instead of using a BM25, could use something else to kind
Yes.
of rank it. So
Yes.
is it just something automatically done, or it depends on the kind of data that I'm searching
It
for?
depends on your eval set, right? So BM25 is also like 25%, let's say, weightage to your keyword search and 75 to your vector search. It depends how you, and that is also a hyperparameter, right? How do you define what is the right value? So that is why it is most important to start with the eval set, and that is your source of truth. Like quantitatively, if you get good results on that, you should be happy. If you're not, that means that you're not happy with your eval set. So first work such that you have a good enough eval set. But in real life, when we want to work on a small project like this, we did not really create an eval set, but we should have. And it's not just like the retrieval algorithm, but then also the re-ranker, which is a very important part when you want to build real world retrieval algorithms, especially using these kind of RAG techniques. So re-ranker is an advanced concept, but you have, I think, the option of enabling it in your assignment. And the
Yeah.
re-ranker is essentially doing like, so, because in your context, you cannot put, let's say, the top 100. So then which one should you then rank between them? And there's a pairwise similarity model trained, which is a much smaller model than your embedding model. And this is why you're able to run it on so many pairs. But yes, like what to use, which search algorithm to use, which retrieval algorithm to use, depends on your eval set.
Okay. Okay, got it.
Because only then you can get a quantitative number.
Yeah, no, that makes sense.
Good.
Yeah, one question, Arjun.
Yeah, brother.
So in that assignment, whatever we have seen is that basically it is searching the vector database and listing out the citations one after another. But if we go to normal ChatGPT or even Gemini, what we see is that again, like if I say like I am like a class 12 student, then it will take all those details and then it will cite in such a way that I understand. And again, if I say like I am an advanced doing PhD, then it will put together the information in a different way. So after whatever you have done after that, what else will be there in
No, see, like
actual
LLM.
GPT kind of model? Yeah, LLM.
No, see, so it's very simple, right? Like the LLM only has two inputs, context and prompt. That is it. That is your conditioning and your, current input. That is it. There is nothing else. So
No,
now,
how do
hmm,
yeah?
go on.
Like how does it present the information in a different way based on whatever prompt that we put?
Yeah, correct. So whatever you retrieved, you can use that as context. You can put that into the LLM as context, and then you have a prompt. And the prompt is then the generation part. It is then massaging your context and doing whatever you want with that, right? It can summarize it. It can ask, like answer questions based on it, because that is how the LLM is trained. So those are the only two levers you have, your context and your prompt. Did I answer your question, or like you wanna rephrase
No, I
it?
was expecting something else maybe there, right, in the model.
No,
Which
there is
will be.
nothing else. There is temperature, but there is nothing else. There is just the prompt and the context. The LLM API has just these two inputs. What else do you want? Like it is a trained model.
Like, how does it organize the data actually, depending upon
It
my?
doesn't organize the data. There is no magic going on. Like it is just the context. So in the context, you can put in data. So when you do your retrieval, that is your precursor. So because you can only, let's say, put three chunks into your context. You cannot put like the entire database into your context. That is why you're doing retrieval. That is why you're doing
Correct.
re-ranking, because you want to get just a little bit of data. Your the most important data, which you can then put in context. And then the prompt is acting on your context, and the model waits. The model already knows about the universe because it is trained on internet data. It has some specific context that you provided it now, and then you can ask something in the prompt based on what it knows about the world and its weights and what you provided in context, and that's it.
Okay.
Yeah, I think it's very simple. I mean, sometimes we overcomplicate it, but that is all that there is. Danina, you're there? Or yeah, how are you doing? And Kunal, how are you doing?
Yes, Arjun, I am having exams going on, and still
Yeah.
uh, I've made it halfway through the third week,
Oh, that's good.
and it's pretty good. Like I'm clear with all the concepts. Yeah, no
Okay.
question for now.
Oh, that's great news. All right, then. I wish you all the best. Please continue the good work and continue, like I said. Wait. Before we quit, I don't know if you're looking at our social media. Anybody looking at our social media? So I want to show you like what something that we really believe in, right? And like these investors said the same thing, and we posted on our social media. So So these guys, right, like make it exist and then make it good later. So this is what I was also saying in the very first session. So how it started, Facebook, and how it is going. This is some other company, how it started, and how is okay Stripe going. And then this is how these guys started, and this is Airbnb. This is how these guys started, and they are some company, right? So I mean, let's build like first just get started, do the assignments, and then we can like build it some like build real world projects, write research papers, and so on. So all the best, and see you next week. Looking forward. Bye.
Thank you,
Thank
Arjun.
you.
Thank you. Bye.
Thank you, Arjun.
Thank you. Bye.